In today's lesson, we're going to look further at linear relationships. So to recall, when we've tried to determine the slope or multiplier, we've found the rate of change, or again the slope, for every step in the relationship. In order to do this, we need to look at how the y values change with respect to how the x values change. So when we've done this in the past, basically we've looked at how has the pattern changed for every position number. What has the number of tiles been increasing by every time we change a position. Right? That's what we've looked at in the past. In previous examples that we've seen or that we've looked at, the change in x values has always been 1. Right? So we've looked at position 0, then 1, 2, 3, 4, 5, 6, and so on. We've looked at that kind of constant increase in position where the position always changed by 1. So we found the slope by basically looking at just the y values. And if you go back in our previous lessons and look at the tables, you would see that we basically looked at how do the y values change. But what if we're given a pattern where the change in x values is something other than 1? So that means we would be given, say, position 1, then 4, then 7, then 9. Right? We can't just look at the y values because we're not seeing every single position. So we're not seeing what the constant change is going to be. So in order to do that, or to find the multiplier for that, or the slope as they call it, we need to look at a different formula, which is the change in y divided by the change in x. And now you may see this written slightly different in some other cases, where it's triangle y divided by triangle x. This basically means delta y divided by delta x. Delta is just a Greek letter, and all it's referring to is basically saying the change in y. So again, just a different, shorter way to say the same thing. So let's look at an example. Here we see our x values, or you could say position number, if it helps you relate to patterns to algebra, and you could say number of tiles for y. So we're given position 0, 3, 7, and 15. So it's not consistent. We're not seeing position 1, 2, 3, and 4. So we can see that for our number of tiles, what we're increasing by is not consistent. We increase by 15, we increase by 20, and then we increase by 40. So that's not a consistent increase. So you may say, well, then it's not a linear relationship. However, what we want to be careful of is we want to check to see what are the position numbers, or what are the x values changing by. Because if they're changing by a consistent rate and we just can't see those other positions, then chances are it may actually be linear. So if I look from 0 to 3, that's a change of plus 3. We've gone up 3 positions. From 3 to 7, we've gone up by 4. And from 7 to 15, we've gone up by 8. So what we're going to do is we're going to look and see, okay, what is the actual slope here? The m is the change in y over change in x. So in this case, we look at what are the y values changing by. Now here we have multiple different options to pick, right? We have either they're changing by 15 or 20 or 40. It doesn't matter which one you choose as long as you're staying consistent with what the x values are changing by. So what I mean by that is, if you say, well, the y values are changing by 15, then the change in x would have to be, in this case, 3. So we're looking at this pair or this change. Now you could do the same thing with the other pair, looking at how does 20, the change in 20, compare to the change in x, which is 4. Or you could look at a third pair based on the table that we have, which would be 40 divided by 8. So if we go through, the change 15 divided by 3, we can simplify this to just 5. Or you could say 5 over 1, which is basically our rate of change for every one position. Or 20 over 4, which is also 5 over 1. Or, as you can see, probably guess, 40 over 8, or 40 divided by 8, is also 5 over 1, or just 5. So it doesn't matter, as long as it's a linear relationship, it doesn't matter which change in y and change in x you use, as long as you're consistent. And we can see here that the change, when we reduce it down to a single position or a single rate, or a unit rate, you might say, we can see that for every one position, it's changing by 5. And we can see that that's consistent across all the values that we looked at, so we would say that this is linear. If I wanted to come up with an equation for this, y equals mx plus b, again, we should remember that m is the multiplier or slope, which we just found. So y equals, we'll say 5, then the x, our variable. The b is our constant, remember. So we need to find our constant. In order to find our constant is when x equals 0. So again, we can see it from our table, x equals 0, y is 4. So that means our b value is 4. So again, that's where we can look at our table to find that b value. And then we have our equation, y equals 5x plus 4. Let's look at another example. 130, 104, negative 9. And then 1775, 223, and negative 3. Again, if it helps, think of position number of tiles. We want to figure out what the equation is. We can see clearly that this is not a consistent increase, or we're not given a consistent increase based on the values that we have. So we are going to have to do some work. I'm going to look at the change in y over change in x. So basically I'm going to see what are my values changing by. Well, from 17 to 75, that's a change of plus 58. From 75 to 223, that's a change of 148. And from 223 to negative 3, that's a change of, or a decrease of negative 226. So even though these points may be out of order, this system or this strategy will still work as long as we're staying consistent. So from 1 to 30 is an increase of 29. From 30 to 104 is an increase of 74. And from 104 to negative 9 is a decrease of negative 113. So again, as long as we're staying consistent with what changes we look at. So what I mean by that, if I look at this first change, let me just kind of move this all over. If I look at the first change in y, so 58 over the change in x, which is 29, or I may look at the second change, which is 148 divided by 74, or over 74. Or maybe I look at the third change, negative 226 over negative 113. Regardless of which one I look at, if it's a linear pattern, I should get the same m value when I simplify my fractions or my division here. 58 divided by 29 gives me 2. Or 148 divided by 74 gives me 2. Or negative 226 divided by negative 113 gives me 2. regardless of which way we look at it, our m value is 2. So we get y equals, we know for sure it'll be 2x. Oops. Again, if we're taking that consistent pattern or that rule, y equals mx plus b, our equation will be y equals 2x. And then for our constant, or that b value, we need to work backwards. So if I want to work backwards to position 0, I'm going 1 position backwards. I know what my slope is for every 1, which is 2. So if I go backwards, I need to take away 2, which gives me 15. So then that means that my slope, when y is 0, or when x is 0, sorry, is 15. So that means my slope, or my constant is 15. So the equation is y equals 2x plus 15. If we look at an example with negative slope, which we should be familiar with, Haley has 3,000 points in a game she plays. Every turn uses up 50 points. Model this relationship with an equation. Right, so you may need to put this into a table. Right, so we have turns, or number of turns, and then we have points. So you can say it starts off at 0, 1, 2, 3, 4. From the equation, we should see that she has, or starts with, 3,000 points. So at 0 turns, she has 3,000 points. Every turn uses up 50 points. So that means after turn 1, 2,950. Turn 2, 2,900 points left. Turn 3, 2,850. And so on, 2,800. We need to come up with a relationship or an equation for this relationship. Now you may be able to get this right from the word problem because we've talked about or we've looked at these types of examples before, or you can look at the table. This one's not too bad because we see consistent values. So we can see that for every turn when we're increasing by 1, the points change or they decrease by 50, which we can also see from the actual question. In this case, because the x values or the one side is consistent, we don't need to actually go through and figure out the rest because we're going to see that it's the same thing, minus 50 plus 1. Plus 1 minus 50. So we see that consistent pattern. This is what we're used to in our previous examples. So we should be able to determine that our multiplier is negative 50. We're decreasing by 50. Our b value, again, hopefully we can see that in our table. When x is 0, the y value is 3,000. So b is equal to 3,000. And we can also get that from the word scenario because we know we're starting with 3,000 points. That's our starting value. So in our equation, it should be y equals negative 50x for our multiplier and then plus 3,000. Now, some of you may like it written slightly different. You might like to start with 3,000 and then you're minusing 50 for every turn, so minus 50x. Either way works, you're just basically rearranging the equation. So the last question is how long until Haley runs out of points? Now, you can go through and solve this using equations. So basically when Haley runs out of points, this is basically saying y equals 0. So in our equation, instead of y, we would have 0 equals 3,000 minus 50x, or again, the other way, depending on what you used. If I want to get x by itself, so that's what I'm trying to find. Get x by itself, I need to cancel out the 3,000 by subtracting 3,000. Subtract it from the other side as well. One side cancels out. I get negative 3,000 equals negative 50x. To get x by itself, I need to divide by negative 50. Do the same thing to both sides. And I'm left with 60 equals x. So that basically means it'll take 60 turns for her to run out of points. Moving on to another example. So now we're already given the equation, or we're given the table, sorry. So again, we want to come up with the equation. Again, because our table isn't consistent, we're not seeing that consistent change in x and or the consistent x values, we might have to use a different formula for our slope. So we want to see what do the y values change by and what do the x values change by. In this case, y seems to be decreasing by 100 in the first one, 800 in the second one, and in the last one, we go from 100 to negative 2900. So we decrease by 3000. Again, even though you might think, well, it's slightly out of order, that's okay, but we can actually see that we're just continually decreasing, so it's not too bad. On the other side for the x, we can see we're going from 5 to 10, so that's an increase of 5. From 10 to 50, an increase of 40. And from 50 to 200, which is an increase of 150. So again, to help us figure out our m value or our slope, we're doing the change in y over the change in x. Multiple different options that we can pick from. I can look at negative 100 over 5. Or I could look at negative 800 over 40. Or I could look at negative 3000 over 150. Regardless of what we look at, if it's a linear pattern, which in most cases it will be, if we're being asked to find the rule, we should have the same m value, which when we go through and we solve this, we should find that we get negative 20 for every one. So we know right off the bat that our y value or the slope or the multiplier is going to be negative 20. So in our equation, y equals mx plus b, it'll be y equals negative 20, the x value, and then we need to figure out what our constant is. If I'm working backwards in my pattern, if I'm going from 5 to 0, that's a decrease of 5 or 5 positions backwards. If I know that in my normal pattern, I'm decreasing by 20 every turn, if I'm reversing that, then I need to be adding 20 for every turn. Because it's 5 positions back, or I'm looking at 5 positions, it's going to basically be 5 times 20. So plus 5 times 20, which equals 100. So that means that my initial value, or the starting value, would have to be 1,100. So by reversing that pattern, I get a constant of 1,100. So my equation then is y equals negative 20x plus 1,100. Here we'll look at an example where we're given a table, or we're given a graph with some key points. From this graph, I can plot the points. Again, remember, the x value comes first in the coordinate and then the y value. So in this case, the first point here, we can see that x is 0, y is 1. The next point in green here, we can see that the x value is 1 and the y value is negative 2. The next one is 2 and negative 5. Again, we can see this one's a nice consistent increase because our x values are increasing by 1 every time, so that is going to make it a little bit easier to find our equation. So 1 to negative 2, we go down by 3. From negative 2 to negative 5, we're also going down by 3. So because the change in x is consistent, right off the bat, I can say that my m value is negative 3. If we still wanted to keep that same idea of change in y over change in x, negative 3 over 1, but anything divided by 1 is negative, or is the same thing. For our constant, here it's nice and easy because we're already told what our constant is from the table. We can see that when x is 0, y is 1. We could also reason through and look at our graph and say, well, I can see the y-intercept. I can see where the line crosses the y-axis. So this value right here, this point, represents the b value. So I know that then that my b equals 1. So when I go to my equation, it'll be y equals negative 3 x plus 1 for the multiplier and then my constant. For example 6, we're going to be looking at slope as a fraction. Again, we can see a little bit of a consistent increase in the change in x. We're always increasing by 3. However, it's not increasing by 1, so we can't just take what the change in y is. We can still look for it. Change in y, we can see we're increasing by 2 every time. But that doesn't mean that the multiplier or the slope is going to be plus 2, because the x value isn't changing by 1. This basically means for every 3 positions, we're increasing by 2. So to represent that in our slope, we have to use that change in y divided by change in x. When we look at it, 2 is our change in y, no matter what values we look at. And then our change in x will be 3. So regardless of what set of points or what we look at, our change or our slope will always be 2 over 3. If I want to work backwards to find my constant, it does work out nicely that if I decrease by 3 or reverse what the pattern I see in the table is, I get to 0 for my x value. So that makes it nice for what the change has to be on the y. I need to minus 2 on the one side and get to 1. So that tells me what my constant's going to be. So in my equation, y equals 2 over 3 for the fraction, 2 over 3x for my slope, plus 1 for the constant. And there is my new equation, or my equation for this pattern. We look at another example. So even we have a graph now of our pattern or of our relationship. We're going to go through and do the same thing. Plot your points, or we have our points and put the values into a table. X is first, so in this case we can see x is negative 8, or sorry, not negative 8. Negative 10 is over here, so sorry, it is negative 8. So negative 8 for the x, y is 0. We can see when x is 0, y is 2. And when x is 8, y is 4. So we can see that it's not going to be a nice even number. But if we look at our pattern and we know the change in y and the change in x, we can use that to help us figure out what our multiplier or slope is. So for the change in x, we go from negative 8 to 0, which is plus 8, from 0 to 8, which is also plus 8. So because our change is consistent, in x is consistent, the change in y, plus 2, we're only really given one option to look at. If I look at my slope, my m value, change in y over change in x, change in y is 2 regardless of what pair I look at. Change in x is 8, so my slope will be 2 over 8. Now I can simplify this a bit. I can reduce my fraction to make it 1 over 4, or basically 1/4. So I know my m value. To find my constant, there's two ways we could do it. Looking at the table, I can see when x is 0, y is 2, or looking at the graph, where does the line cross? I can see it crosses at 2, so that's going to tell me my constant. My rule will then be y equals 1 over 4 for the slope, the x, and then plus 2. So again, different ways you can find that b value, but the slope again is going to be that change in y over change in x. Lastly, we're going to look at one example with a negative y-intercept. Again, we have our graph. We can take these points and put them into a table. So we can have 0 and -4, so that value, or those coordinates are given to us. We can see the next one would be 2 and 2. Now again, we could find other points if we wanted to help extend this table, because we can see where the line nicely or neatly crosses other values or other coordinates or grid lines. So if we wanted to, we could add extra points or extra coordinates. However, we've seen before when we've been dealing with a linear pattern, as long as we're able to get a change in y and a change in x, we don't really need to have any more information than that. So at the bare minimum, we need to have only 2 points, which we do in this case. We can see the change in x is an increase of 2, and the change of y is an increase of 6. So to figure out our m value, or our slope, the change in y over change in x, we can see y changes by 6, x changes by 2. So for every 2 positions we increase by 6, we can reduce that to figure out what we change by every 1 position. 6 divided by 2 is 3. So again, we can just basically reduce our fraction. For the b value, or the constant, again, there's multiple ways. I can look at the y-intercept, where does the line cross the y-axis, or I can look at the table and see when x is 0, what is y. Regardless of which method you use, we can then write out our formula or our equation, y equals 3x minus 4. So we do have a negative y-intercept here. So again, these examples, the main thing we were looking at is what to do when we have different scenarios when looking at linear relationships, and how do we solve when we have inconsistent values in our table. And we learned a new formula, which was the change in y over change in x for the multiplier. So rather than just looking at how does the y value or the number of tiles change, we now look or refer to how does it change with respect to what the x values change by. So again, slightly more work when it's not a straightforward consistent pattern, but again, hopefully it's not too much work in the end to find those values. And again, for the constant, the same ways we looked at before, either looking for the y-intercept or looking for when x equals 0, what does y equal?